Hello everyone, I welcome you all to the ninth chapter Area of Parallelogram and Triangles. Myself Palak Agarwal and I'll be teaching you this chapter thoroughly. So let's see what we will cover today and what is the definition of the basic chapter. Okay, so area. What is area? A part of a plane enclosed by a simple closed figure is called planar region corresponding to that area, and the figure or the magnitude measure of that planar region is called area. Now, there are terms which are in this definition. Simple closed figure. What is simple? Simple figure means that the figure which is dominated or made by lines or planar. Okay, and closed figure means that starting and ending point are same. Now, the area is the region which is covered by a simple closed figure. Okay, so it's basically the measure of the planar region. This magnitude or measure is always expressed in terms of square in some unit as centimeter square or meter square. Okay, square because area is always two-dimensional. Okay, now if two figures are congruent, then they have equal areas. However, the converse is not true. Equal areas can have different geometry. Now, how is that possible? It's very easy. Okay, suppose you have taken a triangle. Okay, and this is another triangle. Now just tell me, is this congruent? No, but area can be seen because half base into height is the area. So suppose this is 2 and height is 2, and for this is 1 and this is 4. Correct. So half base into height is always same for both. So area is same, but they are not congruent. But if they are congruent, then area will be same. Thus, it's written that converse is not true. Okay, just keep in mind. Now, the planar region formed by figure T is made up of two planar regions formed by figure P and Q. We observe that area would be equal to P area plus Q area because they are the summation of the P and Q region. Okay, so we can further subdivide the areas and total up to form a different planar region. Thus, we conclude that area of a figure is a number associated with the part of plane enclosed by the figure. Okay, and it has two properties. If A and B are congruent, then area of A equals to area of B. And if a planar region T is made up of two planar region areas P and Q, then area of T would be equal to area of P plus area of Q. Correct? Now, figures on the same base. Following are the figures on the same base. DC is the base and two figures are drawn from the same base. So, figures on the same base and between the same parallels. These are the figures which are known as between same base and same parallels because AF is parallel to DC and these figures are bounded between the same parallels and are on the same base. And previous figures were just on the same base. Okay. So you need to understand which type of figure is given to you. Now, these are the examples of the figures on the same base but not between the same parallels. Okay, so they are between the same base, like EF is the base, but they are not. AB and DC are two different parallel lines, correct? So they are figures with same base but not between the same parallel lines. Now, figure on the same base and between the same parallels you have already seen. Now, they are not on the same base but they are between the same parallel lines. So these are also different type of figures that parallel lines are same but base is not same. Correct? Okay, so we have seen four types. Thus, two figures are said to be on the same base and between the same parallel if they have a common base side and a vertex opposite to the common base of each figure lying on a line parallel to the base. Okay, we'll take it slow and we'll first cover the end part. Common base, obviously because it's said that they have same base, so they must have a common side. Common base means common side. And second part, it is said between same parallels means that the point at which the vertex opposite to the common base, okay, the point at which they meet the opposite parallel line lies on the same parallel line. Correct? So note that out of the two parallels, one must be line containing the same base and other one with the other parallel. Correct? Now, we'll just take a small activity. You need to do this if you want to understand what is the same base and same parallels. Now, take a graph sheet, draw two parallelograms, ABCD and PQCD in it. Now, the two parallelograms on the same base, DC, and they are between the same parallels, TC and PB. Correct? Now we'll find the area of these two parallelograms. How you'll find area in a graph sheet? You know, we do it by counting the number of squares covered, and those are not covered or semi-covered, we just leave it. Okay, just do the same and count for both. So we'll get approximately 15 centimeters square, and thus we conclude that two figures with the same base and between same parallels have equal area. Two parallelograms instead. Correct? So this is a conclusion which we draw from activity 1. Let's see activity 2. What we have done, we have drawn a parallelogram ABCD on a thick sheet of paper or a cardboard sheet. Now draw a line segment DE. Correct? Okay. Next, cut a triangle ADE congruent to the triangle ADE dash and AD dash A dash D dash E dash. Just merge it on the side. Okay, in such a way that AD dash coincides with BC. Correct? Now, note these two parallelograms ABCD and DE dash D dash. Correct? So, they are on the same base and they are between the same parallels. So, they both are congruent. Like ADE triangle is congruent to AD, A dash, D dash, E dash. Why so? Because we have already seen that we have just implemented the equal part. Okay, we have just cut out the same part. So, obviously they would be congruent. Right. Now, since they are congruent, we can state that area of ABCD is equal to area of ADE plus area of EBCD, or we can replace area of ADE with A dash, D dash, E dash. So we derive at a conclusion that both the parallelograms are having same area. Correct? So this was activity 1 and 2 to prove you that two parallelograms on the same base and between the same parallels have equal areas. Correct? Okay. Now what does theorem 1 says? That whatever we have learned from the activities, that parallelograms on the same base and between the same parallels are equal in area, and we have already proved that. We can prove it by another method, and this method shows that we can prove the congruency. In the activity 2 we have cut out the sheet of paper, but now we can just literally prove that two triangles congruent, and then we can show that both the parallelograms are equal in area. How so? Because area angle AED and angle BFC are equal because ED is parallel to FC and transversal AF. Similarly, by triple angle both the sides, or by ASA both the triangles are congruent. Proved. Now, if they are congruent, then area would be equal, and we'll just using the same, and we have arrived at the solution that both the parallelograms are of equal area. Now we'll solve just a small example to ensure that the theorem is clear to you. Let's do it. We have given an area, a parallelogram ABCD, correct? And also another EFCD is a rectangle. Now, can you tell me one thing? Just pause me out and first read the question, and then I'll ask you something. Okay, so what I was asking to you was, EFCAD is a rectangle. Is a rectangle a parallelogram? Just tell me, yes or no? Obviously, yes. I hope you know that. Correct? Now, we have just learned that, and we will use it here. ABCD and EFCD. CD is common base. Okay. And also CD is parallel to EB. So this proves that area of ABCD is equal to EFCD, and first one is proved. We have already proved how the area of two parallelograms between same base and same parallels are equal. Okay, we don't need to prove that again and again. We just need to use the theorems. Okay, so first one is done. Now see the second one. We have to prove that ABCD area is DC into AL. Now tell me, what is the area of EFCD? Its height into, what is the area of rectangle? Length into breadth. Correct? So what is length? ED. But ED and AL both will be equal because we have just drawing a point, a line. Correct? So we know that AL is equal to ED. Since we have just drawn a parallel line between the same parallels. Correct? Parallel to ED. So area of rectangle EFCD would be ED into DC, and we can replace ED with AL. So area of rectangle EFCD would be DC to AL, and since we know that both areas are equal, so area of ABCD could also be equal to DC into AL. hence proved. Correct? Okay. So we'll end it here. I hope the theorem is clear to you and the basic concepts of the chapter. From next part, we would be moving to the parallelograms on the same base and between the same parallels. For today, we will be stopping here. Thank you so much.